Okay, we're getting into chapter 4, and this deals with partial differentiation and the topic of functions of several variables in general. Okay, one of the first topics we're going to discuss is the limits involving multivariate functions. Okay, and in order to start that discussion here, what I'm going to do is remind you of the formal definition we used in Calculus 1 for limits, right? Now, here I've got the limit as x approaches a of f of x equals L, okay? So basic Calc 1. We're just doing a review here. Do you remember the formal definition, the so-called epsilon delta definition? It said that for every epsilon greater than 0, there exists delta greater than 0, such that, that's what that ST is, such that the absolute difference between the function and the limit is less than epsilon whenever we get sufficiently close to a. Okay? Sufficiently close is represented by this part. Okay? Technically, the absolute value of x minus a is less than delta. Over here, I already have this circled here. Do you know what this implies here? Okay? 0 is less than the absolute difference between x and a. This is basically just saying what? X is not equal to a. Now, you should remember that for a definition of limits here. The limit as x approaches a, do you remember we did not care what was actually happening to the function at x equals a, okay? The function might not even exist at x equal a. Okay, and that's being reflected in this definition right here. Okay, now let's come down here. We'll talk about this graphically in a second. Another thing, here's a way of rewriting this, by the way, if you want to get rid of absolute values everywhere. Okay, this is just saying f of x is being locked between what? L plus epsilon and L minus epsilon whenever what? X is between a plus delta, a minus delta, and here I have to throw this in as an extra condition, x not equal to a, okay? All right? Graphically, what did that mean here? Well, if I imagine the graph of the function y equals f of x here in 2 dimensions, so in the xy plane here, here's my value a right down here, and then let's suppose the function evaluated at a is actually the y-coordinate of that point right there. Do you see that point in black here? This actually has what? It has a discontinuity at x equals a here. Okay, but does it have a limit as x approaches a? It does. Here's the limit, in fact. If you notice here, here's L. Okay, if I was to draw this along here, okay, here's y equals L. Anyways, so the limit is going to be L because no matter how close I want to get to L, I can always do it so long as what? I'm sufficiently close to A. All right? If I had a smaller, tighter value of epsilon, that would make, sometimes people call this an epsilon tube. All right? The set of all y values in points in this tube here have y values between L minus epsilon and L plus epsilon, okay? So long as we're close enough to A, the function values always lie within that epsilon tube, and that's got to hold for what? Any epsilon that is positive, any epsilon greater than 0. Okay, you remember that concept from Calc 1? All right. Probably do. Functions of 2 variables. Okay, let's talk about that then. Functions of 2 variables here. So let's suppose I'm dealing with this situation where I have z being a function of 2 variables, z equals f of xy, over some set of r squared. What is r squared? I just mean here really what the xy plane. Okay, so what we do is take our x and y values from the xy plane, or we imagine them being points in the xy plane, And then what? We evaluate this function at a particular point, and that gives us a z value. We could technically plot this whole thing as what? A bunch of points, x, y, z in space. Now we're going to see here, as we proceed through the chapter, that most of the functions that we'll be looking at of this form, nice, well-behaved functions of x and y, yield a set of points, z equals f of x, y, that is a surface in 3 space, okay? So generally, something like this is going to end up being a surface in 3 space, okay? Alrighty, let's talk about something else here. In preparation for limits, the delta open disk, okay, open disk centered at AB, okay, notice that I've got what? I'm not just don't have x equals a, I have x equals a and y equals b here, technically, right? You looking at that? The delta open disk centered at AB is the set of all x, y, such that the magnitude of the vector from AB to xy is less than delta, okay? Again, I'm going to assume delta is greater than 0. Alrighty? All right, this is going to play a role analogous to this thing up here, okay? This thing up here. Only this is going to be in 2 dimensions here, okay? This is I've drawn in here, this is what I mean by the point difference there. Okay, I actually do this in some of my other classes. I didn't do it in this online class, but the difference between 2 points is simply that vector. And you guys remember how to find the magnitude of the vector, right? The square root of the sum of the squares, okay? All right. But basically, this is just simply saying the following, that the distance from xy to the point AB is less than delta. So what does a delta open disk centered at AB look like? Well, it looks like this, okay? So I've got an open circle because I have what? A less than sign there, a strict less than sign. The radius of this circle is actually delta, and I'm taking all the points on the inside. So you see I've tried to shade it in there like that, okay? That's what we would call an open disk in the xy plane, an open disk in the xy plane, okay? Delta's got to be greater than 0. That's the radius of the circle. If the radius is 0, you're not really dealing with what we would call a disk, okay? Okay, one other thing I'm going to talk about is the punctured delta open disk or punctured open disk. Okay, what did I do here? I took all the values xy or points xy that what? Whose distance from AB is less than delta but greater than 0. That's all I'm doing here. Now there's only one point whose distance from AB is equal to 0. That's the point AB itself. So do you see what I'm talking about when I talk about the punctured open disk? Okay, a punctured open disk, what do? I'm just coming in there and knocking out that little, putting an open hole right there at AB. Do you see what I mean? Okay, that's what so I punctured the disk at AB. That's the punctured open disk. It's analogous, by the way, to what we were doing right up here with this. We would say that's maybe a punctured interval, wouldn't we? That's what we were using in our definition of limit in Calc 1. So punctured open disk. Okay, you don't have to say delta every time. It's a punctured open disk. Let's talk about the limit then. Okay, our limit definition. The limit as xy approaches AB of the function xy equals L if what? For every epsilon greater than 0. Okay, so this is a tolerance, right, that I'm willing to accept in the difference between my function and its limit. There exists a delta greater than 0 such that the function value differs from L by less than epsilon whenever what? xy lies within what? The punctured open disk of radius delta. Okay? So what is just saying, if you get close enough to AB, the function values around it will always be sufficiently close to L. Okay? Again, if you didn't like absolute value signs here, you can get rid of those and just say the f of xy is between L plus epsilon and L minus epsilon on a sufficiently small punctured open disk centered at AB. Okay? Now, if you understood that, okay, again, we're not interested in what happens to this function at AB. Could you go to 3 dimensions, and if I had a function of x, y, and z is equal to L, and say x, y, z approaches ABC, could you give the definition for 3 dimensions? Okay, or even higher. Could you do that? Okay, there we wouldn't call it a punctured open disk, we call it an open ball, or a punctured open ball centered at ABC. Okay, I'm sure you could probably do that then. Now, let me explain here. If you've been doing the reading in the book, you know that most of the limit properties that you've been dealing with from Calc 1, like the limit of the sum is the sum of the limits, or the limit of a difference is the difference of the limits, the limit of a product is the product of the limits, the limit of a quotient is the quotient of the limits, so long as the limit in the denominator is not 0, and so forth. Those basic limit laws that you know from your reading still apply here. Okay? So if I'm going to do something very simple here, I'm going to take the limit as xy approaches 1, 2 here. Now, I'm not going to use the formal definition right now. Okay? So let's not be afraid of that thing. We will do a couple of these with the formal definition. But right now, just say I was going to take the limit as xy approaches 1, 2 of x squared plus 2xy minus y squared. All this would basically amount to, in the end, is evaluation. Okay? Let me explain right now here. Now, we're going to talk about continuity of functions of several variables here later and stuff. But let me explain here. This is just a polynomial in 2 variables here. Just like a polynomial in a single variable, they're always going to be continuous. Okay? So to find the limits, you can always do that by simply evaluating. Now, what I actually did was go through the various steps here and break down the limit using the limit laws that you know from your reading here, and that intuitively you probably know anyways. The limit of the sum is the sum of the limits, so I broke this into what? A sum of 3 different limits. I brought the negative sign on the outside. You can do that. The limit of a product is a product of the limits, or if you have a constant, you can bring that on the outside. I brought the constant 2 on the outside. Okay, so this makes pretty good intuitive sense, hopefully. The limit of a product is a product of the limits, so that means it holds for powers, right? Okay, for natural powers at least. Okay, and then I broke down the limit x y equals the limit x times the limit y, and broke this down into a square. Okay, what's the limit as x approaches, or the limit of x as xy approaches 1, 2? Well, this is just approaching 1. This is approaching 1. This is approaching 2, right? The limit as of y as xy approaches 1, 2 is just simply 2. Okay, substitute those in there, and it's pretty easy here. Okay, alrighty. So that's pretty easy here. Here's a different sort of limit here. Okay, the limit as x of y approaches 0, 0 of the sine of xy over xy. Something you can do in situations like this is, do you see it would be really nice here if I just replace this by a different variable, which I'm going to call z. Okay, now z approaches 0 if and only if both x and y approaches 0 here. Okay, let's just let z equal xy. I'm actually looking for this limit. The limit as z approaches 0 of the sine z over z. And you remember from Calc 1 that actually ends up being 1. Okay? So, as z approaches 0, at least one of these approaches 0. And that'll actually be sufficient for us here. The limit as xy approaches 0, 0, and we get 1 for our limit. The limit as xy approaches 0, 0 of x cubed y cubed over x squared plus y squared. I'm going to leave that as an exercise for you to think about here. I'm actually going to do it in the next lecture so that you will be not left empty-handed. But that's something you might think about in the meantime here, and see if you can use the limit definition to actually work that out. Let's talk about a different limit here. The limit as xy approaches 0, 0, okay, of xy over x squared plus y squared, okay. Now, something I want you to be aware of as we go through this, beware and unaware. When we were talking about, let's maybe come all the way here, when we are talking about a limit as x approaches a, say, in Calc 1, you could only approach a from two directions, right? You could approach from the left or from the right, or from above or from below, right? There's only two ways to approach a, okay? But do you notice when you get to what? A function of several variables, there's actually what? How many ways to approach AB? There's actually infinitely many ways to approach AB, okay? Do you see what I mean? You could be approaching all different directions, okay? Because you've got all this elbow room around you now, okay? Does that make sense? Okay, you could be approaching various directions. Now, here's the idea here. The limit as xy approaches AB of f of xy is going to exist and be equal to L if the limit is L regardless of how you approach AB, okay? So you always have to get that same limit, L, regardless of how you approach that point AB in the xy plane, okay? Alrighty, so that's going to be a powerful notion here. Let me show you here. Now, we're just approaching the origin in the xy plane, right? Let's go ahead and approach along a particular line, y equals mx. This is what? A line with slope m that goes through the origin, right? This isn't even considering vertical lines. And I want to show you something, okay? Suppose I am approaching along the line y equals mx then, and our limit here, xy approaches 0, 0 of xy over x squared plus y squared, would be the same as the limit as x approaches 0 of what? X times what? Mx, since that's what y is when we're approaching along this line, over what? Mx quantity squared. Okay? Now, let's just do a little algebra here. The numerator is actually what? Mx squared. The denominator is 1 plus m squared times x squared. Now, x is approaching 0. We don't care what happens when it equals 0, right? We're not going to be concerned about what happens when it equals 0. Okay, so what I'm going to do when x is not 0, I'm going to imagine canceling this. Okay, I'm just treating this like a Calc 1 for now. As the x squareds will cancel, what happens as x approaches 0 of m over 1 plus m squared? Do you see that this is not constant? This is not independent of the direction in which you're approaching. It's not independent of m. This limit actually does not exist. Okay? Now we'll be doing some graphing here and you'll see this sort of thing. The limit is xy approaches the origin of xy over x squared plus y squared does not exist, is the answer. D, N, E. Okay? Now in this case, I didn't even consider what was happening if I was approaching the origin along the y-axis, right, vertically, because I didn't need to. It's already messed up here, right? It's already clear that this limit doesn't exist. I don't need to engage in that overkill, right? All right? Okay, well, that's just sort of a short introduction here. We'll continue with another lecture along these lines here. In the meantime, you might consider this problem, which will be answered in the next lecture. Okay?